Hey guys, tonight we drift back, way back into the foggy past of everything you've ever known. You're not standing on solid ground anymore. You're floating inside a silent, cold cloud of gas and dust, light years wide. No planets, no sun, just frozen molecules, drifting lazily through the galaxy like forgotten confetti after a cosmic parade. The stars? Too far. The warmth? Non-existent. You're surrounded by stillness, so perfect, it's almost a lie. But not for long. See, deep within this vast, lazy cloud, something shifts. Gravity, quietly persistent and patient as ever, starts to pull. Particles begin to gather, like shy guests at a party no one wants to admit they're attending. Collisions begin, gentle ones at first, like dandelion fluff bumping into velvet. But gravity doesn't do gentle for long. This cloud is collapsing, slowly folding in on itself, building pressure, building heat. And right in the center, something stirs. You, floating through this forming nursery, are now inside what's called a molecular cloud. They're enormous, often spanning hundreds of light years, and this one has reached its breaking point. Shock waves, maybe from a nearby supernova, have nudged the gas just enough to overcome internal pressure. That's when the real collapse begins. Denser regions fall inward, heating as they go, and the core, the very heart of this cloud, starts glowing dimly. You're witnessing the birth of a protostar. This infant sun doesn't shine yet, but it's hungry. It's gulping down matter like a sleep-deprived toddler inhaling breakfast. And with every bite it spins faster. Conservation of angular momentum, baby. Same reason figure skaters spin quicker when they pull their arms in. Only here, instead of sparkly tights and ice, you've got plasma, gravity, and radiation trying to murder each other. Scientists still argue whether the original cloud that birthed our sun was solitary or part of a stellar sibling group. Some believe our sun had sisters, maybe even hundreds of them, formed at the same time from the same stellar womb. If so, they're long gone now, scattered across the galaxy like estranged cousins at a family reunion you don't remember attending. Zoom out a little, and you'll notice the collapsing cloud isn't symmetrical. It's not neat. Turbulent eddies form. Clumps of matter swirl like chocolate chips in cookie dough. As the cloud flattens into a spinning disk called a protoplanetary disk, the center gets denser and hotter, compressing under the crushing embrace of gravity. You're watching a transformation from formless drift to disciplined chaos. And here's where it gets oddly beautiful. The entire system is radiating infrared energy like a sleeping beast. If you could see in that spectrum, it would glow like embers under a blanket. But invisible light? It's still hidden behind thick curtains of dust. The only way to spot such a star in the making is with powerful space telescopes, like peering through a fogged-up bathroom mirror with night vision goggles. Fun fact for you. The earliest material forming around the newborn sun contains aluminum-26, a radioactive isotope that decays relatively quickly. Some scientists think this might have come from a nearby supernova just before our system formed, seeding our region of space like a cosmic sourdough starter. That's right, our solar system might be sprinkled with the ashes of a dead star. Romantic, huh? As more gas and dust spiral into the infant sun, temperatures at the core rise past 10 million degrees Celsius. That's when the real magic happens. Nuclear fusion. Hydrogen atoms begin fusing into helium, releasing energy that counteracts the crushing gravity. It's the cosmic version of standing up to a bully and saying, "Enough, the sun is born." But don't cue the triumphant music just yet. It's still got issues. It's unstable, throwing tantrums in the form of violent solar winds and eruptions. Its light is weak compared to its future self, and its surroundings are still packed with leftover junk. Think of it as a newborn flailing in a messy nursery full of sharp Lego bricks. Meanwhile, that spinning protoplanetary disk around the sun, it's not just decorative. Within that chaos, planets are about to start forming. But for now, all you see are dust grains sticking together, whispering to each other, "Let's do something stupid." It's slow, clunky, and violent. And just like that, the silent gas cloud that started this story is gone, transformed into a radiant star and a swirling arena of debris. It's the end of stillness, the beginning of structure. And somewhere in that debris field, you'll eventually get a blue marble with cats, coffee, and the internet. But not for a few 100 million years. Take a moment to appreciate this. You exist because a cold, forgotten gas cloud collapsed on itself out of pure boredom and became something capable of dreaming. The sun is awake now. It's not lounging. It's not stretching. It's screaming. You float near its blistering surface, just close enough to feel the fury, without being reduced to cosmic ash. The young star is volatile, brighter than it should be, angrier than you expect. It hurls out bursts of charged particles like it's trying to shoo away the mess it was born into, a tantrum made of plasma. This stage, it's called the T-Tari phase. Imagine the sun as a teenager with identity issues, spewing solar flares while belching out ferocious winds, gale forces of raw particles blasting away at the remaining gas in the disk. That's its way of saying, I need space. Literally. The sun hasn't settled yet into the stable nuclear fusion rhythm it'll maintain for most of its life. Inside, hydrogen atoms continue to fuse, releasing energy at a rate that stabilizes its gravitational collapse. A balance is emerging, slowly, between the force trying to crush the sun and the energy trying to blow it apart. But it's not there yet. The furnace is still finding its setting. Meanwhile, that swirling disk of debris around the sun, it's glowing faintly with infrared light. You've got silicates, metals, and ices dancing together in a slow spiral, colliding, breaking, sticking. You're watching a thin soup of cosmic leftovers, but don't let the poetry fool you. This place is chaos. Here's the kicker. The disk isn't just randomly spinning around. It's doing something smart. Material closer to the sun is moving faster, dragged by stronger gravity. Farther out, things slow down. This speed gradient causes friction. Friction causes heat. Heat causes chemistry. And chemistry causes, well, eventually you. And here's a weird one. Scientists think that right about now, as the sun begins to carve out its final shape, magnetic fields start sculpting the behavior of gas in the disk. These fields twist and loop, creating gaps, channels, maybe even influencing where the planets will form. It's like the sun is secretly playing SimCity, planning future neighborhoods before anyone arrives. But we're not there yet. Right now the disk is thick with promise. Tiny dust grains are forming complex silicates. Some are melting, cooling into little glassy spherules called chondrules. These will one day be found in meteorites, but for now they're just tumbling around like confetti in slow motion. Here's your mainstream science fix. This phase, about 4.567 billion years ago, is when the calcium-aluminum-rich inclusions CAIs formed, tiny heat-resistant minerals that represent the oldest solid material in the solar system. You can actually touch pieces of this era today by holding a meteorite. That's like shaking hands with the dawn of time. But not everything goes according to plan. Solar winds are thinning out the disk's gas. The sun, in a fit of photonic rage, is evaporating the surrounding cloud from the inside out. And while the inner disk, closer to the sun, is warm and dry, farther out it's cold enough for ices to survive. This temperature line is called the frost line, and it divides the destiny of worlds. Inside it you'll get rocky planets like Earth and Mars. Outside, gas and ice giants. Scientists still argue whether this frost line moved over time or stayed put like a mood ring locked on a lukewarm. But one thing's for sure. It's a key factor in why Mercury is a scorched peanut while Neptune is basically a frozen fart. So as the disk evolves, the stage is being set. In the inner regions, metals and rock-forming minerals condense. Out past the frost line, volatiles like water, methane, and ammonia start to freeze and stick. Particles begin colliding. Some shatter, others cling. Static electricity might be playing matchmaker, helping grains latch onto each other like shy 8th graders at a school dance. Here's a fun, borderline fringe idea. Some researchers think lightning, yes, space lightning, within the disk might have superheated dust clouds, accelerating the formation of those chondrules. Imagine sparks cracking through a newborn solar system, briefly lighting up dust storms like cosmic paparazzi flashes. Anyway, the collisions continue. Small grains become pebbles, pebbles become rocks, rocks become kilometer-wide planetesimals. And planetesimals? Well, they're hungry. These bodies start to dominate their orbital neighborhoods, sweeping up material like Roombas with rage issues. Every collision is loud, brutal, and full of drama. Think less peaceful accretion and more high-speed demolition derby. The sun, watching all this from the center, continues maturing. Its core reaches equilibrium, outward pressure from fusion balancing inward gravitational pull. It finally settles onto the main sequence, where it'll stay for around 10 billion years. This is the era we live in today. But back then, it was a milestone, a coming-of-age ceremony. like getting a driver's license or your first existential crisis. Our newborn sun is now stable, warm, predictable. Everything else? Still absolute mayhem. But out there, among the chaos, baby planets are forming. In fact, some may already be finished, only to be torn apart by later collisions. This early solar system is not a place of mercy. It's one long montage of creation and obliteration, of hot messes turning into real estate. One final strange twist to leave you on. Astronomers studying disks around other stars have noticed gaps and rings, structures we once thought were unique to our solar system. Turns out, these patterns of dust and emptiness might be universal. Our solar system wasn't just born, it was sculpted. And so, with a settled sun and a disk on the cusp of building planets, you float quietly above the wreckage, listening, maybe for the sound of the first world beginning to whisper. You drift now through a storm of rubble. It's not silent anymore. Every direction pulses with motion. A gritty ballet of dust and rock, pebbles the size of fists, boulders the size of cities, all moving on elliptical tracks, crashing, ricocheting, spinning. There is no up, no down, only orbit. This is the real beginning of planetary formation. Welcome to the age of planetesimals. These aren't planets, not yet. They're the raw ingredients, fragments of matter that have bulked up past dust status and started attracting their own fans, literally. Their gravity is now strong enough to pull in other particles. The big start getting bigger. The small get eaten or thrown aside like popcorn kernels in a blender. This whole process, it's called accretion, a lovely word for cosmic cannibalism. Planetesimals don't ask nicely. They slam into each other at terrifying speeds. Some collisions are soft, like two wet snowballs fusing on impact. Others are so violent they shatter both bodies into 1,000 molten shards. Still, the overall trend is toward bigger and rounder. These misshapen clumps, ranging from the size of a mountain to that of a small moon, are the first planetary embryos. Scientists call this stage oligarchic growth, which makes it sound like a sketchy political thriller, and honestly, it kind of is. A few large bodies begin dominating the rest, sweeping up everything in their gravitational territory. They grow rapidly, claiming regions of the disk like warlords in a broken land. One by one, they knock smaller neighbors into submission or obliteration, and you're watching this all unfold in slow motion. In the inner solar system, close to the sun, it's too hot for ices to survive, so the available building materials are limited to rock and metal. This means the forming planets here, like Earth and Mars, end up smaller and denser. Out past the frost line, however, it's chilly enough for ices to hang around. That means more mass, more material, more ambition. The seeds of gas giants are forming, but we'll get to them soon enough. Right now, the inner solar system is a messy construction site. You float past a forming world, an embryo, maybe half the size of Mars. Its surface is lava, not because it has a core yet, but because of sheer violence. Every few hours, a planetesimal smashes into it, releasing enough kinetic energy to liquefy entire continents. There's no time for cooling. It's chaos, stacked on chaos, wrapped in vaporized rock. And here's a quirky little nugget. Some researchers believe certain regions of the disk had pressure bumps, zones where gas and dust naturally clump together more efficiently. These bumps might have sped up planet formation in some areas, and slowed it in others, like pockets of gravity behaving like secret backstage passes. And while we're talking weird, did you know some planetesimals may have briefly generated their own magnetic fields? If they were large enough to have molten cores, even for a few million years, they might have had tiny temporary dynamos, little magnetic auras flickering through space like nervous ghosts. Meteorites we find today carry traces of these ancient fields, like fossilized whispers. As these growing bodies gain mass, their interiors begin to heat up, not just from impacts, but from radioactive decay. Short-lived isotopes like aluminum-26 are doing the heavy lifting here, generating heat that melts the interior of these protoplanets. This allows heavier elements like iron to sink, forming early cores, while lighter silicates float upward. It's planetary differentiation, and it means these worlds are starting to organize themselves from the inside out. This matters, because it sets the stage for geology, for tectonics, for magnetism, for magnetic fields that will one day shield fragile atmospheres from solar wind. All of that begins here, in this messy, molten stage of planetary adolescence. But don't get too attached. Some of these young worlds won't make it. Scientists still argue whether dozens of Mars-sized bodies formed in the early solar system, only to be obliterated or absorbed by larger ones. It's likely that Earth swallowed a few of its peers in its rise to prominence. Every planet you see today is, in essence, the winner of a cosmic battle royale, and the scars are everywhere. Craters on the Moon, pockmarks on Mercury, the tilted spin of Uranus. These are not quirks, they're bruises, evidence of a brutal time when planet building meant destroying. One last thing before you drift forward. The early solar system was fast, much faster than you'd think. In just a few million years, these planetesimals appeared, collided, merged, and began shaping the very layout of the planetary orbits we have today. In human terms, that's like going from single-cell organisms to skyscrapers in a week. So here you are, drifting through a fiery junkyard that's slowly assembling into something remarkable. Dust became rock, rock became bodies, bodies became battlegrounds, and the real drama hasn't even started. You drift now through a war zone, and you're about to witness the most personal, catastrophic event in Earth's entire existence. Earth is being born, but it's not some serene delivery in a warm hospital room. No blankets, no lullabies. This is the cosmic equivalent of a back-alley bar brawl with sledgehammers and flamethrowers. Earth's formation was brutal, loud, and almost didn't happen. It starts as a planetary embryo, a young, molten thing, barely holding itself together. Gravity has gathered enough mass to make it spherical, and its core is already separating. Heavy iron sinking inward, lighter silicates floating to the top like foam in boiling soup. There's no solid crust yet, just a roiling ocean of magma that stretches from horizon to horizon. Lightning crackles across a choked, toxic atmosphere, and the sky is permanently red, thick with carbon dioxide, hydrogen sulfide, and volcanic rage. This Earth wouldn't welcome you. It would instantly kill you with a mix of lava vapor and radiation, a spa day in hell. Still, it's your home, or at least it will be, if it survives what's coming next, because now, drifting silently toward Earth like a celestial wrecking ball, is Theia. She's a Mars-sized planetesimal, traveling at tens of thousands of kilometers per hour, and she's on a direct collision course. There's no dodging, no deflection. The gravity of Earth and Theia has already sealed their fate. They're going to hit, and when they do, it will be one of the most violent impacts in the entire history of the solar system. Scientists still argue whether Theia formed nearby and got gravitationally nudged into Earth, or if she migrated from much farther out. Either way, she wasn't invited to the party, but she's going to change everything. The impact is not a gentle kiss, it's an obliteration. Theia slams into the young Earth at a shallow angle, maybe 45 degrees, sending molten rock and planetary crust flying into orbit. For a moment, Earth is split open like a cracked egg. Both cores, Theia's and Earth's, partially merge. Debris, still molten, forms a disk around the smoldering planet. This isn't just carnage, it's creation. From that disk of incandescent debris, a new celestial body begins to form. Gravity pulls the ejected material into clumps, which coalesce into a sphere. You're watching the Moon being born, our planet's accidental twin, made not from calm or careful planning, but from planetary trauma. It takes just a few hundred years for the Moon to fully form, and it's hot, so hot it glows. From Earth's surface, if you could stand on it, which again you couldn't. The Moon then begins drifting outward, pushed away by tidal forces like an awkward X being shown the door, and it keeps drifting. Even today, it's still slowly receding from Earth by about 3.8 centimeters per year. One day, it'll be so far away that total solar eclipses will no longer be possible, so enjoy them while you can. Now here's a fascinating side effect of this cataclysmic impact. It might be the very reason Earth ended up habitable at all. Without the Moon, Earth might have spun too fast or tilted too far. The Moon helps stabilize our axial tilt, preventing wild climate swings, and controls the tides, which will one day stir early life into movement. Some scientists even argue that Earth's atmosphere and ocean chemistry were altered by the Moon's formation, creating just the right balance for organic chemistry to ignite. Of course, there are fringe theories too. One suggests Theia didn't just hit Earth, it merged with it almost completely, becoming part of Earth's interior and delivering rare isotopes that influenced our magnetic field. Others propose the moon didn't form from Earth at all, but was a captured object, later shaped by tidal forces into a perfect partner. These theories aren't mainstream, but they do highlight how much of this era is still murky. What we do know is this: after the moon formed, Earth entered a quiet phase, and by quiet, I mean only semi-apocalyptic. The magma oceans began to cool, crust began to form, thin, unstable, and constantly recycled by impacts. Volcanic outgassing created an early atmosphere, rich in CO2, ammonia, methane, and water vapor. No oxygen yet, just a toxic soup that would have fried your lungs faster than a microwave burrito, and the rains began. For centuries, maybe millennia, the skies poured water onto hot rock, hissing into steam and falling again, over and over, until the basins filled. The first oceans, hot, acidic, and deadly, began to blanket the planet. Fun fact, the water that formed these early oceans may have come from multiple sources, some from outgassing, some delivered by icy asteroids and comets. Even today, scientists debate how much came from space and how much was homegrown. But however it got here, the result was the same. Earth, a molten wreck, was now wearing a blue veil. Beneath that veil, something miraculous was brewing. But for now, Earth just sat there, steaming and sullen, spinning slowly under its new companion, the moon. And that companion? It had settled into a perfect dance, locked in synchronous rotation, always showing Earth the same face. A reminder, every night, of the impact that almost ended us, and somehow, instead, gave us the sky. Now that Earth survived its skull-cracking debut, let's pan out a bit. You're drifting toward the sun again, skimming over scorched plains, jagged shadows, and airless worlds that never had a chance to become blue and cozy like Earth. We're in the inner solar system now, home to Mercury, Venus, Earth, and Mars, 4 rocky siblings born from the same dust, but raised by wildly different circumstances. Let's start with the weirdest, Mercury. It's tiny, not quite a planet, and not quite a rock with ambitions. It's more like a metal cannonball with abandonment issues. About 85% of Mercury's volume is just its iron core. That's absurd. For comparison, Earth's core is only about 15%. Scientists still argue whether a massive collision stripped Mercury of its original crust and mantle, leaving it with just a metallic skeleton. Others think it simply formed that way, an iron-rich anomaly in a region of the disk with fewer volatiles and silicates. Whatever the cause, Mercury ended up with a surface that's been baked, bombarded, and cracked like an old skillet left in the fire. It has no atmosphere to speak of, just a thin exosphere of atoms stolen by the solar wind. And yet there's water ice hiding in the permanently shadowed craters at its poles. Ice, on Mercury. Because space is full of contradictions. Next in line, Venus. On paper, it's Earth's twin. Same size, same mass, even a similar composition. But in reality, Venus is your evil doppelganger. The surface temperature is hot enough to melt lead. Its atmosphere is made of carbon dioxide so thick it would crush you like a soda can at the bottom of the ocean, and it rains sulfuric acid, which evaporates before it hits the ground. It's basically a steam room designed by a sadist. How did it get this way? Well, Venus likely experienced a runaway greenhouse effect. Early on, it may have had oceans like Earth, but being closer to the sun, those oceans evaporated faster. Water vapor, a powerful greenhouse gas, trapped more heat, which caused more evaporation, which trapped more heat, until the surface became a hellscape wrapped in clouds thick enough to reflect 70% of the sunlight. You could stand on Venus at noon and it would still feel like twilight, if twilight came with hurricane-force winds and crushing pressure. Venus also spins the wrong way. Scientists still debate why. Some think a massive collision flipped it. Others argue it slowed and reversed over time due to tidal interactions. Regardless, it now spins so slowly that a day on Venus is longer than its year. You could literally roast to death before your birthday. Now let's hop over to Mars, which, unlike Venus, gets too little attention from the sun. Mars is a cold, red ghost. It's only half the size of Earth, with a thin atmosphere that can't hold in heat or pressure. But once it was different. You float over ancient riverbeds, dried lake beds, even deltas, all carved by liquid water. Mars had volcanoes, massive ones, Olympus Mons, the tallest in the solar system, rises 3 times higher than Everest, and it had a magnetic field for a while. But being small has consequences. Mars cooled quickly. Its core solidified. Its magnetic field died. Solar wind stripped away the atmosphere. The water evaporated or froze beneath the surface. The planet didn't die all at once. It slowly faded, like a campfire you forgot to tend. Still, there's life in the old Martian dog yet. Seasonal methane plumes, buried ice, whispered rumors of briny subsurface lakes. It may not host Martians building pyramids, but it could still harbor microbial life in cozy underground pockets. And scientists haven't stopped arguing about it since Viking landed in the 70s. And what about Earth right in the middle of these 3 weirdos? Somehow we won the cosmic lottery. Right size, right distance, strong magnetic field, active geology, liquid water, a stabilizing moon, everything just barely aligned. And yet our neighbors are vivid reminders of what could have gone wrong. Mercury shows what happens when you're too small. Venus shows what happens when you're too close. Mars shows what happens when you cool off too fast. All 3 are ghosts of futures we avoided. Here's a quirky detail. All the inner planets rotate on different axes and at wildly different speeds. Earth spins once every 24 hours. Mars takes just over a day. Mercury's day lasts 59 Earth days. Venus, it takes 2043 Earth days to spin once, and it does it backward. It's like the inner solar system is a gallery of rejected prototypes, and their orbits, not perfect circles. They wobble, they shift, they're tugged at by the gas giants farther out, especially Jupiter. Over billions of years, these gravitational nudges shape everything: weather patterns, axial tilts, even the timing of ice ages. The inner planets may seem locked in their dance today, but everything from their spin rates to their atmospheres were forged in violence and molded by delicate balances. So you float above them now, seeing not just 4 lonely rocks but 4 possible Earths, each a different fate we could have faced. And you can't help but wonder, if things had gone just a little differently, would someone be standing on Mars right now, gazing up at a lifeless blue dot? You've admired the rocky planets, now brace yourself for the giants. As you drift past the frost line, that invisible boundary where solar warmth gives up and cold begins to win, everything changes. Out here, the rules are different. There's more material, much more, and it's not just rock and metal. It's gas, ice, volatiles, and all of it is waiting to be claimed. You're entering the realm of the gas giants. First up, Jupiter, the undisputed heavyweight champion of the solar system. It's not just big, it's obscene. If you took every other planet, Mercury, Venus, Earth, Mars, Saturn, Uranus, and Neptune, and combined them, Jupiter would still outweigh them all twice over. It's so massive that its center may experience pressures higher than the core of the Sun. And yet it's mostly hydrogen and helium, essentially a failed star. Jupiter didn't ignite, but it came close, and in the early solar system, that made it dangerous. This gas giant formed quickly, very quickly, possibly within just a few million years of the Sun's ignition. That speed gave it power. As it grew, its immense gravity began sculpting the solar system's structure, tugging, nudging, flinging smaller objects around like a cosmic bouncer at a rowdy bar. Scientists still argue about how Jupiter formed so fast. The traditional view is core accretion. A rocky core formed first, then hoarded gas. But newer models suggest gravitational instability. A massive part of the disk collapsed under its own weight, instantly forming a gas giant. If that's true, Jupiter might have skipped the line entirely and gone full glutton from day one. Jupiter didn't just sit there. It moved. Yes, Jupiter migrated. At one point it likely spiraled inward, plowing through the inner solar system like a wrecking ball, scattering planetesimals, disrupting Mars's growth, and even threatening Earth's survival. This theory, charmingly called the Grand Tack hypothesis, proposes that Jupiter's journey inward, and its eventual reversal outward, thanks to Saturn's gravitational pull, played a major role in shaping the final architecture of the solar system. You float near Jupiter now, and the view is hypnotic. Massive bands of clouds swirl in eternal storms. The Great Red Spot, older than any living thing on Earth, spins like an unblinking eye. Lightning the size of continents flashes inside towering storm systems. The planet radiates more heat than it receives from the Sun, slowly cooling from the fiery chaos of its birth. And the moons. Oh, the moons. Jupiter has over 90 confirmed moons and likely more to come. Some are small, jagged rocks, but others are worlds. Io is a tortured hellscape of volcanoes. Europa hides a vast subsurface ocean beneath its icy crust. Ganymede has its own magnetic field, something no other moon can claim. Callisto looks ancient, unchanged, like it gave up trying. Each one is a story in itself. You'll return to them later. But now, onward to Saturn. It's softer than Jupiter. With a lower density, you could technically float it in a bathtub if you had one big enough and no respect for physics. Saturn, too, is made mostly of hydrogen and helium, but it's slightly more refined, less chaotic. And then there are the rings. Saturn's rings are dazzling. They seem delicate, almost decorative, like the planet was trying to outdo Jupiter's raw power with pure aesthetic flair. But those rings aren't fluffy or permanent. They're made of ice chunks and dust, orbiting in razor-thin bands only a few tens of meters thick. Scientists once thought they were ancient. Now, the debate rages. They might be just 100 million years old, barely a blip compared to Saturn's age. Some theories suggest they formed from a shattered moon, torn apart by tidal forces when it strayed too close. Others propose they're leftovers from Saturn's formation, refined by eons of collisions and sculpted by moonlets that dance along the ring edges. Whatever their origin, the rings are temporary. They're slowly decaying, bleeding material into the planet. One day, Saturn will be bare, but tonight, under the soft hush of stars, it still wears its icy crown. Saturn also has a moon roster that rivals Jupiter's. Titan is the showstopper. Thick atmosphere, methane lakes, and possibly a subsurface ocean. It's so Earth-like in appearance that early observers mistook its smoggy orange haze for signs of life. It might not have fish, but it has weather, rain, rivers, clouds, all made of liquid hydrocarbons. And here's a delightful oddity. Saturn's moon Enceladus spews geysers of salty water from its south pole, reaching into space. These plumes contain organic molecules and hint at hydrothermal activity deep beneath its icy shell, which means down there in the dark, we might be looking at one of the best places to find alien life. But back to Saturn itself, it too helped shape the solar system. Alongside Jupiter, Saturn disrupted the asteroid belt, redirected comets, and may have even helped deliver water to the inner planets. Like massive bodyguards at a concert, they blocked dangerous intruders from crashing the party, though not always in time. Scientists still argue whether Jupiter and Saturn's early dance ejected a fifth giant planet entirely. Some models suggest an extra world once orbited between them, only to be flung into deep space. If true, our solar system is missing a sibling, and somewhere out there, a rogue planet might be drifting alone in the interstellar dark. You hover between Jupiter and Saturn now, gazing at these twin titans. They don't have solid surfaces. You couldn't stand on them. You'd fall through clouds deeper and deeper until the pressure crushed you into atoms, and even that wouldn't faze them. These aren't just planets. They're architects, guardians, wreckers, and their influence, it's far from over. Now you glide even farther from the sun, past the radiant giants and into the dim, frigid outskirts of the solar system. The warmth fades, and the silence becomes heavier. The light is weaker, bluer. If the inner solar system is a wild city center, and Jupiter is its booming capital, then this region is the haunted, half-forgotten edge of the map. Welcome to the domain of the ice giants, Uranus and Neptune. They're distant, quiet, and very, very weird. Let's start with Uranus, the oddball of the family. It's big, 14 times the mass of Earth, and it wears a ghostly blue-green hue, thanks to the methane in its atmosphere, which absorbs red light and reflects the blues back into space. That part is poetic, but it gets stranger. Uranus rolls sideways. Its axis is tilted by a staggering 98 degrees. That means instead of spinning like a top, Uranus spins like a bowling ball rolling along its orbit. For half of its 84-year trip around the sun, one hemisphere is plunged into a long sunless winter, while the other bakes in a dim summer that lasts decades. How did that happen? Scientists still argue. The prevailing theory, a massive impact, possibly with a rogue planet-sized object, slammed Uranus early in its life, knocking it onto its side and scrambling its internal heat flow. This might explain why Uranus radiates so little heat compared to other giants. It's cold in both senses of the word, distant and emotionally unavailable. It also has rings. Not flashy Saturn-style ones, but narrow, dark arcs made of fine particles. And moons. At least 27, most named after Shakespearean characters, as if the planet is trying to maintain some literary dignity while floating sideways through space. Then comes Neptune, the farthest true planet from the Sun, even colder, even darker, and somehow more active. Despite being over 4 billion kilometers from the Sun, Neptune has violent weather, supersonic winds, faster than any other planet, storms the size of Earth, a shifting, roiling atmosphere of hydrogen, helium, and methane. It's like nature decided, distance? Irrelevant. Let's crank this thing to 11. Neptune, like Uranus, is an ice giant. That means it has more elements like water, ammonia, and methane ices in its interior than the gas giants. And its deep blue color is even more intense than Uranus's, a result of subtle differences in atmospheric chemistry, still not fully understood. Neptune also hosts one of the solar system's crown jewels, Triton. Triton is no ordinary moon. It orbits backwards, a retrograde orbit, opposite to Neptune's spin. This means it likely didn't form there, but was captured, probably a Kuiper belt object or dwarf planet that wandered too close. The capture would have wreaked havoc on Neptune's original moon system, possibly ejecting or destroying earlier moons. But Triton stayed, and it's fascinating. It's one of the coldest objects in the solar system, yet it has geysers, plumes of nitrogen gas erupting from beneath its surface. These suggest a geologically active interior, perhaps driven by tidal forces from Neptune's gravity. It may even harbor a subsurface ocean beneath its frozen shell, another candidate for alien life, lurking in an icy underworld. Now here's a twist. Uranus and Neptune weren't always this far out. According to the NICE model, named after the city in France, not the personality trait, the outer planets didn't form in their current positions. Early on they were packed more tightly, but gravitational interactions, especially with Jupiter and Saturn, caused a chaotic reshuffling. Uranus and Neptune were flung outward. Their migration scattered countless smaller bodies, sculpting the Kuiper belt and triggering a cascade of events that we'll get to soon. You're floating in a region where sunlight is a whisper, one where a human standing on Neptune would see the sun as nothing more than a bright star, not much stronger than moonlight on Earth. And beyond Neptune, things only get stranger. You begin to encounter small, icy worlds. Pluto, Haumea, Make, Eris, dwarf planets, remnants of a time before the giants moved, before the chaos. Pluto, despite its demotion, remains a cosmic heartbreaker. It has a heart-shaped glacier, blue skies, ice mountains, a possible underground ocean, and a moon, Charon, so large that the two bodies actually orbit a point outside Pluto itself. They're like a binary system, locked in a lonely embrace at the edge of everything. Some astronomers still argue about Pluto's status. Others are more focused on what might lie even farther out. There's growing evidence based on the strange orbits of distant objects that something massive may be lurking in the dark. Planet 9, a hypothesized giant planet, maybe 10 times Earth's mass, orbiting far beyond Pluto. If it exists, it's yet to be seen, but its gravitational fingerprint may already be shaping the orbits of far-flung Kuiper belt objects. So you drift farther and farther through icy debris, rogue comets, dwarf planets, and long shadows. This region is not empty. It's the solar system's attic, filled with leftovers, secrets, and things nobody thought to clean up. And somewhere, just beyond the last confirmed planet, the solar system fades into interstellar space. The light is almost gone now. But the story is far from over. Now the silence becomes thicker. You're no longer among the planets. You've left the realm of swirling atmospheres and magnetic fields. There are no sunsets here, only the eternal half-light of stars you don't recognize. You're floating through rubble, the aftermath of the solar system's most violent era. This is the late heavy bombardment, and you've arrived just in time for the chaos. Roughly 3.9 billion years ago, everything goes sideways. Objects, big and small, rocky and icy, start slamming into the inner planets like cosmic baseballs in a zero-gravity batting cage. Earth, the Moon, Mercury, even tiny Ceres, none are spared. Craters are gouged out in minutes that will last for billions of years. The cause? Scientists still argue. The leading theory ties back to that NICE model you floated through earlier. When Jupiter and Saturn entered a particular orbital resonance, their gravitational dance disrupted the outer solar system. Uranus and Neptune were flung outward. In the process, they bulldozed through a vast region of icy planetesimals and rock. Imagine a snowplow charging through a quiet parking lot. The sudden shift destabilized the orbits of millions of objects, comets, asteroids, icy chunks, sending them inward in a violent rain that lasted hundreds of millions of years. The bombardment didn't come in a single wave. It was more like a meteorological season. Planetary spring cleaning by sledgehammer. And Earth got hammered. We've lost most of the direct evidence. Earth's dynamic geology has erased nearly every scar from this period. But the moon remembers. You drift over its pocked, bruised surface, craters upon craters, so densely packed in places they overlap like battle scars on an old warrior. The largest of them, like the Imbrium Basin, were carved during this era. We know this because of Apollo samples, those tiny bits of lunar rock you could hold in your hand that still carry the isotopic echoes of ancient impacts. You might think this period was purely destructive, and in many ways it was. Whole regions of the moon's crust were vaporized. Earth's thin new crust melted into lava seas again and again. Mars lost whatever atmosphere it had tried to build. Venus likely got flash-boiled. But destruction, paradoxically, can be creative. Some researchers believe this bombardment delivered water to Earth. Icy bodies from the outer solar system, comets and wet asteroids crashed into our hot young world and vaporized, adding their water to Earth's growing reservoirs. Without them, our oceans might be puddles, or worse, absent. Others suggest the bombardment seeded life itself. Organic compounds, amino acids, carbon chains could have hitched a ride on these space rocks, landing on Earth's surface to mix in with the primordial soup. This idea, called panspermia, suggests life might not have started here at all. It may have arrived. It's fringe, sure, but not impossible. Scientists have discovered amino acids on meteorites, even sugars and components of RNA. One impact could have changed everything. And here's a chilling thought. This bombardment might have also reset the clock. Any early life that began before 3.9 billion years ago, probably wiped out, vaporized, sterilized. Earth was likely habitable before the late heavy bombardment, and then abruptly uninhabitable again, several times. It was only after the chaos waned that life could establish a proper foothold. You float down through that thick, toxic atmosphere, down toward an Earth trying to heal. The crust is reforming, oceans are settling, the sky is still murky with carbon dioxide, but it's stable. The impacts have slowed, not stopped, but slowed enough to let chemistry have a chance. You watch volcanic islands rise from the sea like steam-soaked bones. Rain still falls in endless sheets. Lightning cracks across the sky like a whip from the gods. And somewhere, in a tide pool, or a hydrothermal vent, or a clay-filled puddle, something shifts. Molecules begin to arrange themselves. Patterns emerge. Replication starts. Very slowly, and not always correctly, but again and again, like the universe whispering, try. We're still in the Hadean eon, the era of hell, but the inferno is weakening. The Earth is stabilizing. And in the wake of so much destruction, the building blocks of life are beginning to stack. Not with blueprints, not with intention, but with persistence. Every once in a while, a straggler comet or asteroid still roars through the sky, a flaming reminder that peace here is temporary, always. But compared to the bombardment, this is quiet. The solar system has matured. The planets have found their lanes. The chaos is calming. And you're drifting in a lullaby of ash and memory, because from here, the story stops being about what formed and begins to focus on what survived. The fireworks are over. The sky, though still rusted and heavy with ash, is no longer falling. The crust has cooled. The oceans have settled into deep, steaming basins. And Earth, scarred, scorched, and soaked, is quiet for the first time in hundreds of millions of years. It is within this uneasy calm that something remarkable begins to twitch. You drift closer, drawn not by noise or motion, but by chemistry, in some forgotten corner of the planet, maybe a hydrothermal vent deep beneath the sea, maybe a sunlit pool at the edge of a volcanic island. Carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur start playing with each other. They form chains, then loops, then clumps that fold and wriggle and somehow replicate. This is not life yet, but it is flirting with the idea. Scientists still argue about where this all began. Was it in deep-sea vents, powered by heat and minerals bubbling from Earth's mantle? Was it in warm, shallow pools, where evaporation concentrated the right ingredients? Or was it delivered by comets, jump-starting biology with alien molecules? No one agrees, but everyone agrees on this. Somewhere, somehow, life began. These earliest forms weren't cells yet. more like squishy soap bubbles made of lipids, primitive membranes that could trap and protect their own inner chemistry. Inside, fragile strands of RNA began to copy themselves. Most failed. Some survived. Fewer still improved. But over countless generations, self-replicating molecules evolved into something persistently alive. You wouldn't recognize these early microbes. They had no nucleus, no organized machinery, but they fed, they divided, they adapted, and they spread. The Earth was theirs. For billions of years, microbes were the only life that existed. Entire geological eras passed without a single eye, wing, or spine, just mats of bacteria, layered like lasagna, growing in tidal shallows and deep in the crust. They built communities, stromatolites, which you can still see in parts of Australia today, fossils of Earth's first cities. And even here, Jupiter plays a role. You float back out, away from Earth's delicate surface, and toward the giant gas ball still humming near the frost line. Jupiter is no longer in its destructive mood. It's settled into its orbit, massive and stable. And now, it's become a guardian. See, the solar system isn't empty. It's full of debris, rocks, ice, shards left over from the time before. Some of these stray near Earth's orbit, drawn inward by gravity and chaos. But Jupiter stands in their way. Its immense gravitational pull acts like a shield, deflecting, capturing, or redirecting many of these potential threats. The asteroid belt, for instance, could have formed into a planet, but Jupiter's influence prevented that, scattering the material, keeping it fragmented. And comets, they often come screaming in from the outer reaches, long cold arcs from the Kuiper belt or Oort cloud. Jupiter either swallows them whole, or alters their path enough to miss Earth. Not always. We've still been hit, but far less often than we might have been. It's a cosmic irony. The same planet that nearly destroyed everything in its migration phase is now keeping the inner solar system from being pulverized on a weekly basis. Of course, Jupiter's not perfect. Sometimes, it aims those objects at us. There's an ongoing debate about whether Jupiter is more of a protector or a sniper. Some models suggest its gravitational influence may actually increase the number of comets that intersect with Earth's orbit over long timescales. It's like having a very powerful friend who sometimes forgets where the brake pedal is. Still, without Jupiter, and to a lesser extent Saturn, the inner solar system would be far more unstable. Earth might have been reduced to molten goo several more times before life even had a chance to whisper. Meanwhile, back on Earth, life has begun exhaling. Literally, photosynthetic bacteria have emerged, cyanobacteria to be precise. They take in sunlight, carbon dioxide, and water, and produce sugar and oxygen. At first, this oxygen is just absorbed into the oceans, reacting with iron to form rust-colored sediments. But eventually, the oceans can't hold any more, and the gas begins to build in the atmosphere. The great oxygenation event has begun, and for most existing microbes, it's a death sentence. Oxygen is toxic to anaerobic life. It rips apart delicate cell membranes. For these early life forms, it's an apocalypse. But for Earth's future, it's a turning point. The air is changing. The skies are shifting from red to blue. The ozone layer is forming, shielding life from solar radiation, and the groundwork for complex organisms is being laid. You float above Earth now and see it shimmering, not with cities or forests or birds, but with microbial mats stretching across every coastline. The planet is alive, even if it doesn't look it. Far above, the moon still orbits faithfully, stabilizing Earth's tilt and creating tides, gentle rhythmic pulses that stir nutrients, drive currents, and nudge evolution forward. All the pieces are in place now. The sun is stable, the moon is locked in, Jupiter stands guard, the air is turning breathable, and life is no longer just chemistry, it's biology, and it's getting bolder by the minute. The solar system hums quietly now. It's still moving, of course. Still rotating, orbiting, drifting. But the violence has calmed. The planets have settled into their grooves. The chaos of formation has faded into routine. And within this newfound peace, something delicate begins to unfold. The long, patient story of Earth's evolution, aided, protected, and occasionally sabotaged by the largest planet in the system. Let's talk about Jupiter's role. Not as destroyer, not as guardian, but as architect. Its mass didn't just shape the orbits of other planets, it sculpted the entire layout of the inner solar system. The asteroid belt, that fractured realm of spinning debris between Mars and Jupiter, it's not just cosmic litter, It's what's left of a planet that never formed because Jupiter's gravity kept yanking on the building blocks like an older sibling ruining a Lego project. As you float above it now, the belt seems calm, just scattered rocks drifting in silent loops. But zoom in, and you'll see that it's a buzzing hive of motion. Objects jostle, collide, fragment, and occasionally break free. Some tumble inward toward Earth. Others are nudged outward into long, looping orbits that take millennia to complete. Jupiter causes most of that motion. In fact, it doesn't just tug on asteroids, it sings to them. No, seriously. Jupiter's gravity sets up orbital resonances, zones where objects fall into repeating rhythms. For example, an asteroid caught in a 3-1 resonance with Jupiter orbits the Sun 3 times for every one of Jupiter's orbits. These resonances can be stable, locking objects into place, or wildly unstable, ejecting them into entirely new orbits. It's orbital music, and Jupiter is the DJ. One of the most famous results? The Kirkwood gaps, empty lanes within the asteroid belt where resonances with Jupiter have cleared out all the debris. These aren't random, they're scars, gravitational footprints left by a planet with mass to spare. But Jupiter's influence goes beyond the asteroid belt. Head farther out, and you'll find the Trojan asteroids, 2 vast swarms of rocky bodies trailing and leading Jupiter along its orbit, hanging in place thanks to gravitational balance points called Lagrange points. These regions are stable traps, and Jupiter has hoarded thousands of Trojans over the eons, like a cosmic pack rat. Meanwhile, back in the outer solar system, Jupiter's reach extends even to the Kuiper belt, that icy distant realm home to Pluto and friends. Resonances out there have sculpted Pluto's peculiar orbit, one that crosses Neptune's path without ever colliding, thanks again to a gravitational dance set up by Jupiter's early migrations. And if we go even farther to the very edge of the solar system, Jupiter's early nudges may have helped shape the Oort cloud, that vast spherical shell of icy bodies that surrounds the entire solar system like a loose, cold halo. Most of those objects are too far away to see, but when one gets perturbed by Jupiter, Saturn, or even a passing star, it can fall inward and become a long-period comet. Which brings us to Jupiter's less appreciated talent, playing goalie. We've already talked about its role in deflecting comets and asteroids, but it goes deeper. Jupiter regularly intercepts objects on Earth-crossing orbits. Its sheer mass allows it to either eject these threats into deep space or swallow them whole. You might remember comet Shoemaker-Levy 9, which smashed into Jupiter in 1994. It was torn apart by the planet's tidal forces before impact, and the resulting collisions created Earth-sized scars in Jupiter's atmosphere. For a few days, even backyard telescopes could see the bruises. It was a chilling reminder that space is still dangerous, but also a comforting one, because if that comet had been headed for Earth instead, we might not be here talking about it. Some scientists estimate that without Jupiter, Earth would experience 1,000 times more impacts. Others caution that Jupiter's role is more complicated, that it may increase impacts under certain orbital configurations. Either way, it's clear that Jupiter is no mere background character. It's been actively shaping Earth's survival since before Earth even had continents. And yet, despite all that power, it has no solid surface. If you dove into Jupiter, you wouldn't land. You'd fall deeper and deeper, past cloud layers of ammonia, water vapor, and metallic hydrogen, until the pressure crushed you into something no longer human. Still, you'd be falling through a planet that kept Earth safe, that redirected threats, that helped give life a chance to breathe. Back on Earth, life is getting ambitious. Single-celled organisms have dominated for over 2 billion years. But now, something astonishing is happening. Cells begin cooperating. They form colonies, then complex structures, then true multicellular life. Algae, simple worms, jellyfish-like floaters, drifting through the oceans. The Cambrian explosion looms just around the corner, a surge of evolution so intense it floods the oceans with every basic body plan still used today. Eyes, fins, mouths, spines. Life is no longer passive, it's moving, eating, competing, and every single one of them owes their moment to a sky that wasn't constantly falling. You float back now, far above Earth, above Mars, beyond the asteroid belt, and look toward Jupiter one more time. There it is, striped, swollen, forever spinning. It doesn't care that you're watching. It doesn't know what life is. But by its sheer presence, its gravity, its timing, its endless pull, it changed everything. A planet that almost wiped out Earth might just be the reason Earth survived. You hover in the inky dark now, above a solar system that looks peaceful, almost boring. But you know better. Beneath the quiet orbits and soft reflections of starlight, the system is still alive. And while the chaos of formation has passed, subtle shifts continue. Tilts, twists, rotations that make no sense, worlds doing things they really shouldn't be able to do, unless something weird happened a long time ago. Let's start with the planet that's just wrong. Uranus, you'll recall, is a sideways spinner. It rolls through space like a sleepy croissant, not upright like a proper planet. Its seasons are absurd. For 21 years at a time, one pole basks in constant sunlight, while the other is buried in darkness. Then they swap. Scientists still argue over what did this. The dominant theory is a massive collision, maybe a rogue protoplanet, maybe multiple hits, but some suggest more exotic possibilities. Perhaps Uranus once had a massive moon that altered its tilt, or maybe gravitational nudges from Neptune triggered a flip. There's even speculation that Uranus's own internal heat, or lack thereof, played a role. It's the only gas giant that doesn't radiate more heat than it receives from the sun, a cosmic cold case. Now look to Venus, that sweltering furnace with the acid clouds and rebellious attitude. It spins backwards. Retrograde rotation, it's called, a slow, stubborn roll in the wrong direction. A day on Venus takes longer than its year. For a while, some scientists thought Venus didn't spin at all. Others thought it once spun normally, then had its rotation reversed by strong atmospheric tides or core mantle friction. There's still no consensus. Venus remains one of the solar system's biggest mystery boxes, but maybe the strangest spin belongs to Earth's moon. No, not its rotation, though it's tidally locked, always showing the same face. What's strange is how perfectly it matches Earth's needs. The moon stabilizes our axial tilt, controls our tides, and gently slows our rotation. Without it, Earth might wobble like a drunken top, sending climates into chaos every few thousand years. Some scientists argue that intelligent life may never have evolved without the moon's steadying hand. And yet, the moon is a fluke. Born from catastrophe. A 1 in a billion shot. You begin to sense a theme. The solar system isn't just a collection of planets, it's a gallery of scars. Every tilt, every wobble, every rogue rotation is a clue to a history that's far more dramatic than textbooks let on. Mars, for instance, has 2 misshapen moons, Phobos and Deimos, that look like captured asteroids. But their origins are contested. Did Mars snag them during the chaos of the late heavy bombardment? Or did a giant impact spawn a debris disk like Earth's moon, and they just never formed into anything prettier? Either way, Phobos is doomed. It's spiraling inward, and will either crash into Mars or break apart to form a ring in the next 50 million years. That's right, Mars might one day have rings, like a midlife crisis but with more rubble. And then there's Saturn, famous for its majestic rings, but harboring a mystery of its own. Its moon, Enceladus, is tiny, only about 500 kilometers across, and yet it has a subsurface ocean, geysers shooting into space, and hints of hydrothermal vents. It shouldn't have this much internal heat. Tidal forces from Saturn help, but it's still a puzzle. Same goes for Titan, Saturn's largest moon. With its thick nitrogen-rich atmosphere and methane lakes, it's eerily Earth-like. Some scientists think prebiotic chemistry is actively happening on Titan's surface today, just waiting for the temperature to rise a few hundred degrees. Over by Neptune, Triton spins the wrong way, retrograde like Venus, suggesting it didn't belong to Neptune originally. Its capture would have caused chaos, possibly disrupting Neptune's original moons and altering its rotation. You float past it now, watching nitrogen geysers dance across its frozen plains. A moon of mysteries, adrift in a borrowed sky. All these tilted axes, backward spins, cratered moons, and broken rhythms, they're not bugs in the system. They're features, evidence of a time when everything fought for its place. Even Earth isn't safe from subtle weirdness. Our axial tilt, currently 23.5 degrees, isn't locked in. It wobbles slowly, over 41,000-year cycles. These wobbles affect our climate, ice ages, and even the shape of evolution. The sun's influence, the moon's tug, and gravitational nudges from the other planets all contribute. It's a ballet of forces, keeping Earth on the razor's edge between chaos and calm, and that edge is delicate. If Earth tilted just a few degrees more, the seasons would swing to extremes. Imagine a summer hot enough to boil inland seas, followed by a winter that locks continents in ice. If we lost the moon, or if it never formed, that could have been our reality. No ancient forests, no mammals, maybe no you. So many what-ifs orbit this solar system. What if Jupiter had spiraled too far inward? What if Theia missed Earth? What if Triton smashed into Neptune instead of settling into orbit? What if Uranus never tipped? Each world carries the fingerprint of something improbable, a random roll of the dice that ended up shaping everything else. Even now, billions of years later, those early battles still echo. You drift quietly above the plane of the ecliptic now, watching the planets wheel in slow, elegant arcs. To the untrained eye, it looks stable, but you know the truth. The solar system is tilted, twisted, off-center, and deeply wounded, and somehow, it's perfect anyway. From this height, the solar system looks serene. The planets keep their pace. The moons follow obediently. The sun glows steadily at the center, a middle-aged star pretending it has all the time in the world. But you know better now. Underneath the calm, change never stopped. Because despite what science class might have hinted, the solar system is not static. It's evolving, subtly, constantly, like a living thing growing older, slower, and just a little weirder with time. Let's start close to home. The moon is leaving us. Slowly, centimeter by centimeter, it's drifting away. You wouldn't notice it in your lifetime, but over geologic time, it adds up. When the moon first formed, it loomed enormous in Earth's sky, maybe 10 times larger than it appears now. The tides it pulled were colossal, creating daily tsunamis that scoured continents. Now the moon is receding at about 3.8 centimeters per year. Eventually, millions of years from now, Earth's rotation will slow enough to match the moon's orbit, and both will be locked in a gravitational stare-down. No more total solar eclipses, a quieter sky. Meanwhile, Earth's spin is slowing. Thanks to tidal friction, each day is getting a tiny bit longer. At the time of the dinosaurs, a day was about 23 hours. Go back to the early Earth and you'd be whirling through a full spin in just 6 hours, 1/3 of your current day. Imagine cramming your entire life into a year with 1,400 sunrises. The inner planets are still battered by impacts, but they've mostly settled into routine. Mostly. You float above Mars and the winds whisper a different story. Mars is still changing. Its polar ice caps grow and shrink with the seasons. Dust storms race around the globe. Sometimes something massive kicks up and swallows the whole planet in a smothering red veil for months. But underneath all that, ancient rivers, canyons, and salt deposits hint at a wetter, warmer past, a time when it may have had oceans. Some scientists believe Mars experiences climate cycles tied to its axial tilt. Unlike Earth, Mars has no stabilizing moon, so its tilt can wobble dramatically, sometimes over 60 degrees. That means entire eras where the poles melt, the equator freezes, and ancient ice flows again. And don't write Mars off just yet. Beneath the rusty soil, radar scans have found echoes of liquid water, briny, salty lakes that may be kept fluid by subsurface heat or pressure. Combine that with seasonal methane plumes in the atmosphere, and you've got a mystery. Is something alive down there? No one knows. Farther out, the moons of the giant planets refuse to stay quiet. You pass over Enceladus, a frozen billiard ball of a moon orbiting Saturn. Geysers erupt from its south pole, spraying salty water, organic compounds, and even molecular hydrogen into space. These plumes form part of Saturn's E-ring and hint at hydrothermal vents beneath the moon's icy crust. Earth has those too, and they're full of weird, extremophile life. Same story with Europa, Jupiter's icy moon. Cracked and lined with reddish streaks, it hides a vast ocean beneath its frozen shell. Tidal flexing from Jupiter's gravity likely stirs the water, keeping it warm. NASA plans to visit Europa soon, to sniff its surface, and maybe, just maybe, see if something's moving down there. Even Titan, smothered in orange haze, is changing. Its methane lakes are evaporating. Some scientists think Titan is going through a slow climate shift, maybe even entering its version of an ice age. One day, its atmosphere could collapse or thicken into something even more alien. And Pluto? It's not a frozen rock. It has active glaciers, flowing nitrogen ice, and possibly a liquid interior. The New Horizons flyby revealed a surface that had recently changed. In solar system terms, that's like catching a mountain mid-yawn. And here's the big twist. Even the sun is evolving. Right now it's in a long, stable phase called the main sequence, where it burns hydrogen into helium in its core, keeping gravity and radiation in perfect balance. But this balance is fragile. Every second, the sun fuses 600 million tons of hydrogen. Every second, 4 million tons of mass are converted into energy. And over time, this changes the sun's structure. It's growing brighter, 30% brighter than it was when Earth formed. This slow uptick in luminosity is gentle, but relentless, and it has consequences. In the next billion years, Earth's surface will slowly heat, oceans will evaporate, the water vapor, a greenhouse gas, will trap even more heat. Eventually, the planet will become uninhabitable. Long before the sun goes red giant, Earth will have been cooked dry, Venus all over again. And what about the planets? They're drifting too. Tidal interactions are causing orbital migration. The moon, as we said, is moving out. Mars's moons are moving in. Jupiter's gravity still tweaks asteroid orbits. Saturn's rings, they're falling. Slowly, but definitely. In a few 100 million years they may be gone, just dust in Saturn's upper atmosphere. Scientists still debate how stable the solar system really is. Some models predict that over trillions of years gravitational interactions could eventually eject a planet. Others suggest orbital resonances will trigger new waves of instability. You drift now through a solar system that looks permanent, but is anything but. It's a clock, a ballet, a slow spiraling story of orbits, light, and decay. Everything still moves, everything still changes. Even here at the end of the world, nothing holds still for long. You hover in the fading warmth of the sun, and you can feel the future pressing in. It's not immediate, not dramatic, but it's inevitable, like gravity or taxes. The sun, our gentle anchor, is on a timer, and that timer is ticking down. Welcome to the solar midlife crisis. Right now, the sun is about 4.6 billion years old, about halfway through its life on the main sequence. It's comfortable, stable, quietly turning hydrogen into helium and lighting the solar system like a patient desk lamp. But deep inside, in its core, the fuel is changing. Slowly, the hydrogen is being used up, and the helium ash is piling up at the center. As that helium core grows, the sun compensates. It burns hotter. It shines brighter. You don't notice it day to day, but in geological time, the sun has become nearly 30% more luminous than when Earth formed. And that extra brightness, it's already causing trouble. The habitable zone, the sweet spot around the sun where liquid water can exist, is creeping outward. Right now, Earth still rides within it, but not for long. In about 500 million to 1 billion years, the sun will get just bright enough to trigger a moist greenhouse effect on Earth. The oceans will begin to evaporate, and the water vapor will trap more heat, accelerating the process. Surface temperatures will climb, plants will die, the carbon cycle will collapse, the atmosphere will thicken into a humid, deadly soup, and then the oceans boil, all of them gone. You float above Earth now, still blue, still full of clouds, but knowing its days are numbered. The land will bake, the air will thin, life will retreat underground or vanish entirely. Eventually, even extremophiles will give up. Earth will become a scorched, cracked husk, a second Venus, painted with the memory of oceans, and still the sun will shine. Until one day, about 5 billion years from now, it hits the wall. The core, full of helium, can't fuse it efficiently at first, so it contracts. That contraction heats up the surrounding hydrogen shell, and that starts fusing even faster. The result? The sun expands. Massively. Welcome to the red giant phase. From your vantage point above the solar system, you watch the transformation. The sun bloats, first doubling in size, then growing hundreds of times larger. Its outer layers puff out, its color shifts from white-yellow to orange-red, and its surface cools slightly, even as its total energy output skyrockets. Mercury is the first to go, swallowed whole by the expanding plasma. Venus follows, stripped and consumed. And Earth, it's complicated. Some models say Earth gets engulfed. Others say the sun's expansion slows just enough to leave Earth skimming the edge of destruction. But it doesn't matter. Even if Earth escapes the fire, it won't escape the heat. The atmosphere will be gone. The crust will melt. The surface will be sterilized. The moon, a melted shadow. Mars might warm up briefly. Ironically, its frozen plains may thaw. Its skies may lighten. But it won't last. The red giant sun isn't stable. Its outer layers are unstable, drifting off like dandruff in a solar breeze. The solar wind becomes a solar gale, shedding trillions of tons of gas into space. A planetary nebula begins to form, and then just like that, it ends. The helium in the core ignites in a brief, furious helium flash, fusing into carbon and oxygen. But even that phase is short-lived. The sun isn't massive enough to continue. It doesn't become a supernova. Instead, its outer layers drift away completely, forming a glowing planetary nebula, a ghostly shell of gas, lit from within by the final ember of the sun's core. That ember is what remains. A white dwarf. Earth's star, once a raging nuclear engine, is now a sphere of carbon and oxygen, no bigger than Earth but with half the sun's original mass. It no longer fuses atoms. It simply glows with residual heat, cooling slowly over billions, trillions of years. And that's it. The sun's work is done. You float in the shadow of the nebula, now, its tendrils glowing in soft blues and purples, stretching across space like a memory. The inner planets are gone, or ruined. The gas giants have drifted farther out. The asteroid belt is a whisper. The Kuiper belt is still cold, still intact. The solar system is a graveyard. Its light fades year by year, until eventually it becomes a black dwarf, a cold, dark remnant that doesn't emit light at all, pure theoretical silence. This phase takes longer than the current age of the universe, so black dwarfs don't exist yet. But they will, one day, and maybe somewhere far beyond, someone or something will find this place. They'll see the ruined orbits, the melted moons, the frozen planets, and maybe in the dust, they'll find a tiny petrified fossil, proof that here, once, something looked up at the stars and wondered what came next. The sun is gone now, at least in the way you once understood it. What remains is quiet, a faintly glowing cinder, white-hot, compact and timeless, a white dwarf, cradling the ghost of a solar system that once teemed with motion. But don't be fooled by the stillness. The story doesn't end here, because even in death, gravity plays on. Let's start with the wreckage. Mercury and Venus are long vaporized. Earth is either a scorched skeleton or a memory etched in drifting rock. But the outer planets, Jupiter, Saturn, Uranus and Neptune, they're still there, changed, faded, but there. They now orbit farther from the sun than ever before. As the sun lost mass during its red giant phase, its gravitational grip weakened. The planets responded by drifting outward, subtly, but permanently. Their orbits became wider, more elliptical. The entire balance of the solar system stretched like an old rubber band, and with that stretching came chaos. The gravitational harmony between the gas giants, never perfect, has loosened. Over immense timescales, even tiny imbalances add up. You watch as Uranus, just a bit too close to Neptune, gets nudged. Then again, then harder. Each orbital pass is a gravitational shove. Millennia pass. Eventually Uranus may be ejected from the solar system entirely, flung into interstellar space to drift forever. And it's not alone. Astronomers believe that most stars lose at least one planet after their red giant phase. The orbits destabilize. Worlds are scattered. Some fall inward and are shredded by the white dwarf's tides. Others are cast into the void. Rogue planets, no longer tethered to any star, wandering the galaxy in endless night. Some of these ejected worlds might still carry life, maybe deep underground, maybe frozen in stasis, maybe long gone, but they remain, ghost ships from broken systems, coasting silently through the galactic dark. You float through the ruins now, past the asteroid belt, mostly cleared by time and migration. Beyond it, Jupiter still holds its grip on a few loyal moons, but its role as solar system guardian is over. No more shielding, no more flinging comets away. Now it simply orbits a faded colossus, reflecting the dim glow of a corpse star. Saturn's rings, gone. They were never permanent. Over time, radiation pressure and gravitational drag eroded them. Some particles fell into the planet, others drifted off, forming thin, invisible clouds. Saturn is now ringless, just a pale gas giant, stripped of its former elegance. But its moon Titan, it might still exist. Its thick atmosphere could freeze solid, collapsing into layers of nitrogen ice. The methane seas are locked beneath a crust colder than anything you've ever imagined. But frozen doesn't mean erased. The chemistry is still there. The potential is still there, just paused. Farther out, the Kuiper belt and scattered disk are thinning. Many of their icy bodies have been kicked into new orbits or jostled inward, where they eventually disintegrated. Some fell into the dying sun during its bloated final years. Others were caught in new gravitational resonances, or collided with one another, forming dust. And beyond that lies the Oort cloud, still vast, still deep, still holding trillions of icy fragments, orbiting the sun so distantly that the entire solar system looks like a speck of lint in comparison. These comets, drifting tens of thousands of astronomical units away, still feel the pull of that dark ember at the center, but not forever. One by one, passing stars, wandering through the galaxy at tens of kilometers per second, pass close enough to jostle the Oort cloud. Each close encounter perturbs a few comets. Some fall inward, some are thrown free. You might see another solar system's comet streak across our dead system, an interstellar trespasser, a silent visitor from a neighbor that no longer remembers us. Eventually the Oort cloud will dissipate, not all at once, but over billions of years. Its icy components stolen, scattered, or lost. And when that happens, the solar system will finally be naked, stripped down to the white dwarf, a few loyal planets, and maybe a ragged belt of rubble orbiting close like dust around a forgotten candle. But even the white dwarf is cooling. You float close now, no longer blinding. It's dimmed to a dull red. Over time, it will continue to radiate its leftover heat into the void, losing energy one photon at a time. It won't fade fast. It'll take trillions of years. Eventually, the white dwarf will become a black dwarf, a theoretical object, as the universe isn't old enough for any to exist yet, a sphere of degenerate matter, cold and utterly dark, no light, no heat, just gravity, a corpse that outlived its memory, and with that, silence. But don't be sad, because even this quiet has purpose. That white dwarf, blackened and invisible, still holds the atoms that once powered the sun, still holds the memory of planets, oceans, continents, and microbes that dreamed of stars, still holds calcium forged in flares, iron burned in solar hearts, and carbon exhaled by supernovas long before our own beginning. It is, in a way, the record of everything, not lost, just still. And you float on, orbiting a star that once was, in a solar system that once birthed the only known life in the universe. There is poetry in that, not because it lasted forever, but because it ever happened at all. You drift now through the long dark, far from warmth, far from light. The solar system, once a theater of fire and fury, is reduced to shadows. The orbits continue, but their dance is tired, slow, rehearsed. The white dwarf at the center fades into invisibility. Planets still wheel around it, maybe two, maybe three, silent ghosts of once mighty worlds. They're cold now, their atmospheres frozen or gone, their surfaces locked in endless winter. The sun no longer shines, it remembers shining, and yet movement remains. Even now, even here, gravity keeps the music playing. Moons still orbit dead planets, asteroids still slide along dusty ellipses. The Oort cloud, mostly dispersed, still lets go of a stray fragment now and then, a frozen rock arcing inward toward a center that can no longer be seen. You hover at the system's edge, peering out at the interstellar dark. It's not empty. Far beyond, other stars pass, some still young and hot, others already collapsed into their own remnants. Every so often a rogue planet slides by, ejected from some long-forgotten solar nursery. These wanderers feel no heat, no home, just drift. The Milky Way, our galaxy, keeps rotating. Stars orbit its center in a spiral that takes hundreds of millions of years. Our solar system joins this procession. Even as it fades, it moves around the galaxy, through space, and toward something unknowable. And here's the quiet, impossible truth. This journey doesn't stop. The galaxy will evolve too. In about 4 billion years, it'll collide with Andromeda, two immense spirals merging into one vast elliptical galaxy. Stars will pass like ghosts. Black holes will spiral inward and merge. And somewhere in the aftermath, that cold remnant of our solar system will still be circling, unchanged, unseen, unimportant, and eternal. Over time, the very atoms in our white dwarf might decay. Protons may evaporate. Electrons may wink out. The matter of the solar system may become something else, or nothing at all. But all of that is trillions upon trillions of years from now. Right now, there is only this, stillness, darkness, a memory frozen in orbit. And then, quietly, we pull back one last time. Not just from the solar system, but from the entire idea of permanence. You realize now that nothing built here, no planet, no moon, no ring, no sun was ever meant to last forever. But their stories ripple outward. They echo. Earth may be gone, but its signature, its strange balance of chaos and comfort, remains written in dust, orbit, gravity. Every moment that came after was shaped by the solar system's improbable beginning, and perhaps in some other corner of the galaxy something saw it, maybe even understood it, or maybe not. Maybe we were it. the only ones to witness it from the inside, and maybe that's enough. You exhale, finally, and feel the weight of 4.6 billion years settle on your shoulders like a warm blanket. Not heavy, not cold, just final. So close your eyes, dear traveler. The stars are quiet now. Sleep comes easy in the dark. The journey has ended. The fire has burned low, and what remains is peace. Let your breath slow. Let your shoulders drop. Let your thoughts settle like dust on a forgotten moon. You've traveled across billions of years. You've watched worlds collide and vanish. You've seen stars ignite and fade. You've stood in the cradle of creation and drifted through the graveyard of what once was. And through it all, you floated gently, weightless, untouched, just watching. There's something calming in the idea that everything, even the most violent storm of space and time, eventually softens into stillness, that even chaos has a bedtime. You don't need to remember every detail. Let them slip away. Let the roaring of gas giants and the whisper of comet trails drift to the back of your mind. Let Mercury's scars and Titan's haze blur into distant echoes. Just hold on to the quiet, the vastness, the sense that you are part of something so much bigger than yourself. And now, as your breath eases and the dark wraps gently around you, know that you're safe. The stars may be far, the sun may have died, but in this moment, in this calm, all is well. Sleep easy now. You're home.